So today I'm going to give the first in a series of three sessions, 3 lectures over the next 3 days. And so it's going to be covering different aspects of training deep visual models using limited supervision, right? And I'm going to cover the gamut from somewhat weakly supervised methods, semi-supervised methods, and then also completely unsupervised methods, focusing really on self-supervised learning. So today I'm going to start off with that, with self-supervised learning, and the reason for that is because, as you will see further on, self-supervised learning methods are really found the basis for a lot of what is going to follow in terms of taking these models, what people sometimes call foundation models, and then I'm using them in downstream tasks using approaches such as feature learning or domain adaptation. Okay? So as I mentioned, I'm going to focus today on self-supervised learning. I don't know if I'm going to cover everything today, so we'll see how far we get, and if we have like extra bits to go over, we'll just continue with that tomorrow. So let's take a step back. Let's take a really high-level picture and think about, what are we actually trying to achieve, right? So the goal of a lot of visual deep learning is, especially for vision, is to learn some kind of representation, right? We want to learn a representation using some deep model that's going to be a rich representation and a generalizable representation that we're going to be able to use for a lot of different tasks, right? So in that sense, it's somehow generalizable. And so typically, when we're learning such a representation, what we do is we take some samples. So for example, this image, and then we use it as input. We're going to throw it into some deep model. That's going to give us, as an output, some representation that we're then going to throw into some sort of loss function that we're going to use to assess like the quality or the fit of this model. And then using the loss that we get out of that, we're going to use that to update the parameters of the model, right? For example, using backpropagation. So that's the example, I showed for one example, but of course we're typically going to do this with many examples, because the more examples we see, the richer and the more generalizable the representation will be. So as you would imagine, given that we really need all these different examples to train a robust representation, the amount of examples we have is super important, right? And specifically for vision, we're pretty lucky because we have visual data is super abundant, right? Like cameras are everywhere, they're all in our phones right now, and we can find them all over the internet. So there's really a lot of visual data we can capture, and that's going to help us to learn very rich representations. So that's really the 60,000 foot view, but diving a little bit deeper now, let's look at a couple different paradigms for learning. So a very sort of basic one is what we call unsupervised learning applied to deep vision. And so in that case, once again, we have our paradigm with a bunch of samples that we're throwing into some model. In this case, when we have a deep model, you can think of a deep model as being composed of a feature like a visual representation piece, i.e. a feature extractor, that's going to give us some sort of vectorial representation of our image. And then we're going to have some predictor. Some function that's going to give us throughout a prediction of interest. And normally we train these two things jointly, so you can think of it as one unified model. And so given that this model includes a predictor you're going to have as output some sort of prediction. And for unsupervised learning tasks, normally the prediction could be something like a cluster membership, because very classically, unsupervised learning, one such unsupervised learning problem could be clustering, or it could be something like image reconstruction. There are many different things that you might want to predict in this paradigm. And so once again, once you have a prediction, you can apply some sort of loss function to it to assess the fit of that model, and then use that as a signal to update it. So what are some good things about this paradigm? So the good thing is that we don't need any labels, right? So that allows us to leverage as much data as we have, basically, right? As much unlabeled data as we have. We don't need to worry about having and collecting annotations for it, and that's really a big positive of this type of approach. But of course, one negative is that it's not optimizing for any specific downstream task, right? Unless you're actually interested in clustering your data or in reconstructing your data, if you want to use this as simply an approach for learning a generalizable representation, then this is not going to necessarily optimize for that. You might get a fairly suboptimal representation. And of course, with this type of approach, you can't really leverage supervised learning objective functions, right? By definition, they require some sort of supervision, usually in the form of labels that are annotated, that are collected by humans. And that's a pity because supervised learning is probably the most standard paradigm we have for learning, for statistical machine learning, and it's a very rich field and a very successful field. So it's a bit of a pity that we can't really use these types of objective functions. So kind of on the other extreme, we have, of course, supervised learning, where once again, we're trying to learn some model, and this could be exactly the same architecture. But in this case, the prediction might be something that might be a few different things, right? So we might want to predict something like a label in a classification problem. Or if we're thinking of object detection, we might want to predict the bounding box around some object of interest. And you can think of many, many, many more examples. But the key thing here is that compared to what I was just showing before, in this case, we're going to take this prediction and compare it to some ground truth, right? And by ground truth, I mean by something, a label that has been assigned by a human to be the target value that we want to predict, right? So for example, in this case, this is an image of a jackal. Actually, I think this is from South Africa, from last time I was here. And we want to predict what is for example, the species of this animal, right? So assuming you don't really get it right, the model doesn't get it right, then this gives you some loss, and then you use that loss to update your model. By the way, I didn't mention, if anybody has any questions, feel free to stop me at any point. Just raise your hand if something's not clear. So the great thing about this is that this allows you to optimize for a lot of target prediction tasks, right? So for example, for classification, for object detection, and these are very often tasks of interest. So it's great that we can optimize for directly by simply having human supervision. But I mean, there's a flip side to that, right? Of course, on the one hand, yes, you can use humans to kind of steer the learning, and that's great. But on the other hand, you need humans to steer the learning, right? And that's not easy. Collecting a lot of annotated data is very time-consuming. It's very laborious. And if you think beyond simple tasks like classification into something like object detection or image segmentation, it takes a lot of time for humans to do these things correctly, right? And there's like a kind of long tail of very tough problems that are very difficult for humans to annotate, and it becomes very infeasible to collect things this way. And lastly, so one thing that's not great about this is that it's not going to allow us to leverage data that doesn't have annotations, right? So compared to the previous case with unsupervised learning, you can't really do anything with data if there aren't any annotations attached to them, right? So that's a pretty significant drawback of this. And so this is where self-supervised learning comes into play. So by the way, how many of you are familiar with self-supervised learning? Great, okay. So that's where it comes into play, where it's very similar to supervised learning, but in this case, we do collect some kind of quote-unquote ground truth. But in this case, the ground truth is going to be generated by the data itself, as opposed to having a human in the loop to create these annotations. And what's great about that is that it allows to leverage label-free data, because the data can kind of generate labels itself. And it can also leverage supervised learning objective functions. So when you have some notion of ground truth, then you can plug that into your typical supervised learning loss functions and learn, as you will see, very effective representations that way. One negative, though, is that as with unsupervised learning, it's not necessarily going to optimize for some target task, right? But you'll see that there are quite a few ways to mitigate that as we go through the next slides. So that hopefully motivates a bit why self-supervised learning is a really interesting, let's say, entry point into this, the kind of spectrum between unsupervised and supervised learning. So now I'm going to spend a fair bit of time just taking you through different pretext tasks, like different ways of collecting these different annotations without having humans in the loop. I'll discuss a bit also of certain typical architectures that we use for these models. And then I'll spend in the last bit some time just discussing how we evaluate these models. Because as I mentioned, because they're trained on pretext tasks, we have to think carefully about how do we actually evaluate the quality of these models. And I'll show you some examples later on. So just to back up a bit, so self-supervised learning, as I mentioned, it's extremely related to supervised learning, as you can imagine, right? So you think you would have seen some of this earlier in Ferentz's talk. So assume you have some training set D, which is a set of pairs of x's. So let's say input samples, this can be an image, and y, where y can be some label. And in this case, we have n such samples. So you can think of this as n images assigned with their labels. And when I say y, I mean, I use the term label, but it's a bit of an overloaded term. So label doesn't necessarily have to be just, for example, a category label. It can be something pretty complex, right? So a label can be something also like a bounding box, coordinates, or it could also be an actual full image segmentation, pixel-wise segmentation as well. So you can think of this y as something that can potentially be quite complex. And so you're given this set of samples. You're also given some function g, parameterized by theta, and this is typically a deep model. And you want to minimize the following loss with respect to the parameters theta, right? So simply this is some loss that measures the fit or the lack of fit between your function and the labels of interest, the target labels, and you want to minimize that using empirical risk minimization, as you guys saw earlier. So with self-supervised learning, what we're going to do is, rather than have these ground truth labels collected by humans, denoted by yi up there, we're going to collect some kind of pseudo-ground truth, denoted by pi, and then we're going to create this new training set. So this training set is going to be pairs of xi, pi, where pi has been sort of generated automatically. And by the way, I'm putting it here fairly simply, having sort of one ground truth associated with an instance xi. However, you'll see that there are maybe most of the approaches I'll show can generate a potentially infinite amount of pseudo-ground truth as well. So there's potentially, many more, much more than just one pseudo-ground truth per sample. And yeah, so once you have that, then you just, you can use for the same sort of learning objective that I showed before. In the first case, you're just using yi as your targets, and in this case, you're using the pseudo-ground truth as your targets. So as I mentioned, these PIs, these pseudo-ground truth, they're going to be generated from so-called pretext tasks. It's called pretext tasks, as the name implies, right? Because it's sort of, these are meant to be tasks that are thought, that where the intuition for them and the motivation for them is to be tasks that will allow the network to learn things that are also useful for the kinds of target tasks you'd be interested in. So things like classification or object detection, etc. So that means that they should be useful for learning versatile representations that can be used for a variety of different tasks, and that they should be pretty enriched. So let's get our hands dirty. So why don't we start going through a few of these approaches. So I'm going to start off with a work by Dosovetsky et al. From NERVS 2014. And this is a method that proposes, right, as a pretext task for producing labels that are useful for learning representation, to learn to categorize different patches taken from an image. So this is a pretty simple procedure. I'll walk you through it. So let's say we have some unlabeled training set, right, just a collection of images, no human annotations whatsoever. What we're going to do is we're going to sample a set of image patches from these images, okay? So let's say we sample n patches, right? And these can be, this is an illustration taken from the paper of different patches. And you can see they're not very small, right? They're sort of like correspond to things like small objects or parts of objects. And then once we have these patches, for each patch, we're going to take one of them, and then we're going to generate a set of transformations of that patch, right? So using, let's say, for example, you can have potentially an infinite number of transformations. You're going to sample some of them, k different transformations, and you're going to apply them to this patch that you selected. So here you're seeing an example here on the bottom right. So the top patch, which has this red border around it, is the original patch. And then you can see that in this work, the authors propose a bunch of different ways to transform that patch to give you some sort of diverse set of these patches. And so they did things like slightly rotate it, so maybe take the image and rotate it 5 degrees one way or the other, change the color scheme a little bit, and they might have done a few other things. And what this does is it starts to give you a set of images, or a set of augmented, you can call it, patches, for each of the original patches you had, right? So you started off with n patches. For each of these patches, you apply k different transformations. And what that gives you at the end is a training data set of n times k samples, right, where there are n categories, right? Because basically what you're doing is you're trying to create a classification problem out of this task, where each class corresponds to a patch, and then you have k samples of that patch, i.e. category. Any questions, feel free to put up your hand. Right, so as I mentioned, what we're going to do is we're going to treat each of these sets of transform patches as a class. So for example, in this case, we have one class, and then we have n such classes, right? Each of them having k samples, k examples for you to train from. And then once you have that, you train with the objective function you see here. So this looks really similar to what I showed before, right? This is sort of just cropped from the paper, but you can see it's exactly the same. You have like a loss function, which is computing some sort of measure of fit between your label I, which in this case is the index of the patch. So the patch is a category label, and then the transformed version of the sample of the original patch, right? And then you compute this loss for every augmentation of every patch, right? So you sum over n times k numbers, and this is your loss, right? It's a classification loss. And so what you saw, yep? So, good question. So if we use a whole image, then, well, I guess that you can do it, but the point of the patches, I guess I would say, is to, number one, allow for more diversity, right? So for example, if you take a whole image and you just have that one image, and then you can make transformations over the image, like maybe you rotate it a little bit, maybe you change the color, but you're still going to have the whole image. If you take patches from the same image, that allows you to, you can imagine how you're going to create a much higher amount of data, right? A larger quantity of data. Because if you have an image that's 500 by 500, and you're taking out of it like 96 by 96 patches, the combination of different patches you can create are much higher than if you're just trying to augment the full image. That's one thing. The second thing I would say is that, as I was mentioning before, I feel like if you're trying to augment a full image, the augmentations are going to be pretty minimal. So as I mentioned, you might rotate it slightly. You might make certain modifications to the color scheme, but it's not going to be quite as diverse, I would say, as if you were sampling different patches. That's the motivation I would give for it. It's not like my work, but I think this is some of the trade-offs. You will see, though, that there are some methods that I'm going to show in the future which will have transformations over the full image, and you will see that that actually can be quite effective as well. So, right, so this is the first approach. It's pretty simple. Oh, yep.
Thanks. And how do you know what patch to cut out, so you're preserving information relevant?
Yeah, that's a good question. So I don't believe that in this work they spent a ton of, I don't think they put a lot of, I don't want to say thought, but I don't think they mentioned much about spending a lot of time trying to find particularly informative or useful patches. However, so I think they just sort of randomly chose patches. That being said, it is a great question, right? You can imagine that, let's imagine you had an image where a lot of the image was sky or something. It was just not very informative. You may not want to select that patch. And I'm sure somewhere out there there's a work that investigates that. This particular work I don't think did, but it is a great question, yeah. Because you might want to decide, okay, if I have many, many patches to choose, I'm going to choose ones that are a bit more informative than other ones. So that's one. So let's move over to another one. So I'm just going to kind of give you a sense by going through a few examples of some of the kinds of pretext tasks that have been proposed in literature. So this might seem a bit of jumping around, but that kind of reflects the reality. So this next one is about predicting context. And this is going to be one in a line of a few works that are going to be really trying to focus on localized information so that you can have representations that are even richer. Because one thing you'll see, I don't know how many of you are familiar with computer vision generally, but it's generally the case that if you want to perform a task like classification, like classifying a label, the information you need to do that task can be pretty globalized. Whereas if you want to perform a task that is, let's say, pixel level, for example, image segmentation, then you're going to have to be able to encode a lot of very localized information, naturally speaking. And so some of these methods will really try to be geared towards the latter. And this may not be super clear yet, but when you see some examples further on, I think it'll become clearer. So in this case, the goal here is to predict relative positions of patches. Okay, so the procedure is as follows. So you take this, a large data set once again, unlabeled, not necessarily, you're not using any labels whatsoever. Then you throw a grid on top of the image, a 3x3 grid in this case. Then from each cell in that grid, you're going to sample a patch from the cell. And the reason why you're not just going to take the patch itself, but you're going to sort of perturb it a little bit, is just so that you can be robust a bit to sort of artificial, so artifacts of the boundary, right? Because very often, like a neural network can kind of hyper-focus on boundary artifacts and learn things that way, which you don't want. So it's just going to crop somewhere between that grid. And once it has, and then once you have that grid, you're going to sample 2 cells. And then what the task that you want to predict, to perform, is to predict the position of the second patch relative to the first, right? So let's imagine you picked here, as you see the example, the kind of, let's say, middle of the face of this cat. And then you're given the second patch, you want to be able to predict, oh, okay, that patch belongs in position 3, right? And the intuition here is that having a model that's able to perform this task is going to result in a representation that's quite rich and encoding a lot of sort of localized information. And so just to touch a bit on the architecture, I won't really go into it, but it's just to say that the way this is actually sort of implemented as in terms of a model is that you have these 2 patches. They're thrown into 2 convolutional networks to give you 2 different vectorial representations, I think of size more or less 4K. You can aggregate them somehow, and then once you have this aggregated representation, that's a mix of the first patch and the second patch, you just throw a classifier on top, and then you train this classifier to predict the relative position, okay? And this, once again, I think it's a pretty intuitive approach, and it does perform quite well on certain downstream tasks, right, the target tasks of interest. So the next one in this line, this is work that, as the name suggests, to predict rotations from Gedaris et al. And so you were asking this question about, why not use the whole image? So here's an example where the whole image is used. This is super, super simple. I really like this approach. And the goal basically is you take an image, you rotate it, one of literally 4 ways, right? You either actually don't rotate it, or you rotate it like 90 degrees, 180 to 70. You take your rotated image, you put it as input into a convolutional network, and then you simply predict the rotation, right? So you say, okay, I have this image as input, by how much was it rotated? And you're not trying to predict some real value. You're actually, this is a four-class categorization problem, right? Where you have 4 potential rotations. And that's it. And this model performs quite well, actually. So it actually outperforms some of the earlier works we were seeing. And this tells you, once again, that the judicious choice of a so-called pretext task can really pay a lot of dividends, right? Because this is very easy to implement, very simple, pretty light as far as things go computationally. You don't have to be, throwing a bunch of different patches into a network. That's quite expensive. And then it performs quite well. Just to touch a little bit on this one, I'll touch a little bit on the performance just because I think it's kind of nice milestone work. So in this work, to evaluate it, the comparisons were made between a model that was trained in a fully supervised manner on CFAR10. So CFAR10, I think it was also mentioned earlier, it's a data set for image classification where you have 10 classes. It's typically used for evaluating these types of things. And so you can either train a model using the full data set from CFAR10, or you can train a model using the self-supervised approach I just showed, right, of the image rotations. You can use the model that was trained in the self-supervised way to initialize the weights of your final model, and then you take that model that you just initialized some part of it, you throw like a classifier on top of it, and then you train the full thing, right? So you can not train the full thing, you simply just train the new layers, right? So what you have at the end is one model that's completely fully supervised, and another model that's sort of semi-supervised. You have some of it that's been self-supervised and some layers that have been fully supervised, okay? And then what this work showed is that if you look at this supervised model, it's a specific architecture called network and network, and the full supervised model performs quite well. And then you see that this model, where it's partially supervised, actually reaches performance that's not too far from it. But I think perhaps more interestingly, you can see the effect when you reduce the amount of training data that you have, okay? So if you look at this graph, I'm going to walk you through it. So you're seeing here two graphs, right? So the first one in blue is the graph that shows test accuracy, so how well the model is performing on classification on this CFR10 data set. And then you're showing the accuracy as you increase the number of training samples, right? So let's imagine this data set has, I think, 5,000 training examples. What happens if you reduce the number of training examples to only 20, or to 100, or to 400? As you would expect, if you reduce the amount of training data, the test accuracy decreases quite a lot, right? The model is not really able to learn an effective model with the limited amount of data. However, if you look at the semi-supervised case, where some part of the model has been trained using self-supervision, and then another part has been, a smaller part on top has been trained with full supervision, you can see this model is much more robust to having limited training data because it already has a good initialization and it can perform pretty well, even having seen only, for example, 20 training images. Yeah.
Here, the number of training examples, it only refers to the supervised part. Right?
Yeah, exactly.
Unsupervised part still has...
It still has, I think in this case it was supervised with CFR10, so it would have seen the whole training set, but not the labels. Yeah, so I'm speaking only of the labels. Yep. Okay. So the next approach is that I'll discuss is image colorization. So in here, the task is to take as input an image that is grayscale, you can say, where it has only lightness information, and then to predict the color channels based just on the lightness channel, right? So the task here, in other words, is to generate a plausible colorization for an image without any color in grayscale. Okay? So that's what you see illustrated here by the schema. You have like some convolutional network. The input is going to be this lightness channel, right? So for those of you who may not be familiar, so typically an image is represented as in RGB with 3 channels, right? Red, green, and blue. Or sometimes there are other color spaces you can use, right? So typically in the literature, you might see color spaces like YUV, it's more typical for video. Or for a lot of perceptual problems, you might see another color space that's called LAB. But they're all just different ways of representing color images. Okay, in this case, the authors use what's called the lab space. And the goal here is you have the lightness channel, and you're just producing a color channel. Okay? And so how do they do this? So the approach was to predict for each pixel in the original input a distribution over a set of potential colors that the pixel can take. Okay? So to do this, they took the color space, right, which in this case is, it's just a 2-dimensional space, you could say, because the lightness, they're not focusing on the lightness aspect, so you just have A and B. So you can think of this as some sort of 2D space, right? And then what they do is they just quantize the space. They construct a grid over the space. And then they're going to say, okay, for each of the locations in this grid, I'm going to predict the probability that the color of the pixel belongs in this grid, okay? Now, the grid is not like, it's not every element in the grid is valid, so you're going to get a subset of cell values. And what this means in practice is that you're going to have 313 in this case, because of the specific quantization of the color space. You're going to have 313 potential colors that the pixel can take. And then you're simply going to learn to predict a probability over those colors, right? So basically, you're going to get a 313-dimensional probability distribution. And once you have that, so basically what you're going to predict are these logits, Z. Sorry, I don't have a pointer, so I hope you guys see me. So you're going to predict a set of logits Z, and then you're going to normalize them such that it gives you a probability distribution using some sort of damping function, like parameter T, temperature. And then you're going to, the point estimate you're going to make of the color is going to be the mean of that distribution, okay? And so what you have, like, just to wrap up, is for every pixel location, you're going to have a predicted color, and then you're simply going to compare the predicted color to the ground truth. And once again, you can see that this ground truth is really easy to collect, because what you need an image that is a color image, and then you you can sort of decompose the image into the lightness aspect and the color aspect. You use the lightness aspect as input, and you use the color aspect as your target, okay? And I believe, yeah, so in this work, the authors used the mean squared error, and they use that as their loss. So moving on for a tour, another I think, interesting work is to predict permutations. So in this case, you see folks who are just having fun with different ideas. So, and they work quite well. So in this case, once again, you have a grid over an image. And it's a bit similar to the case we saw before where we wanted to predict relative context, right? So you have one patch and you want to predict the relative position of another one. In this case, you're kind of taking another step beyond, and you're saying, if I have this grid, I'm going to once again sample from cells in each cell in the grid. This is going to give me, in this case, 9 different patches. I'm going to permute them, right, to create some shuffle version of them. And then I'm going to predict the permutation that was used. Okay, so I'm going to try to be able to sort of reverse this permutation. Okay, so this is actually, once again, I think conceptually very simple, but a very difficult task actually. Like, it's hard to train a model to actually do this 100%. I think it comes maybe around 80%. And it's actually, it allows for training a representation that's quite rich. And by rich, I mean very performant, right? It's going to encode a lot of information that's used for different downstream tasks. Just to go into this in a bit more detail, once again, you have your grid. You sample patches from within each cell. And you choose a permutation. So you can, of course, there are like many different permutations you can make. What this work does, which I think makes a ton of sense, is to select 1,000 different permutations, right? So just sample among all the permutations that are possible for just 1,000 of them, and treat them like categories, right? So you're going to have, and so given this set of permuted patches, you're going to run them through a network. Each patch goes through the same network to give you a representation. You're going to combine the representation from all these patches. I think they're concatenated, right? And then once you have the representation, you put a classifier on top, and that classifier is going to categorize this input into one of, I think, 1,000 different permutations, okay? So this is a relatively expensive model. I think there are probably relatively efficient ways to encode it, but at its core, you can see that it requires, running a convnet 9 times. But it is a very effective representation. No, I don't think so. And this performs, as you would probably imagine, it performs better than the version we were seeing before, the method where we had just the context prediction, where you just had a pair of cells from a given grid, and you wanted to predict the relative locations, right? And that's because, I mean, intuitively, right? It's not like theoretically proven, but the intuition kind of makes sense in the sense that because this is a more complex task, because you're actually trying to solve, to some extent, this full jigsaw puzzle, in order to perform this well, the representation has to be even more rich and even more informative than in the previous case. By the way, what's the time? Do you know? Thanks. Okay, so now we're going to go into some examples that are more tuned towards video understanding, right? So they're going to be trying to leverage temporal structure in sequences. Okay, so then you'll see some things play around with the idea of how can we gain knowledge from the order in which sequences of frames appear. And the first one in this line is about verifying temporal order. Once again, I would say pretty intuitive. And so in the end, what we have is a binary classification task, which is going to be applied on tuples of frames. So we have, I think, 3 frames. And we want to predict whether the frames are temporally ordered or not, whether they're correctly ordered, right? So are they ordered by temporal progression, or have they been shuffled in some way with respect to time, okay? So one thing that the authors felt important to note in this work is that when you have videos, it's potentially the case, maybe often the case, that you have some portion of the video that's just where not a lot of motion is happening. So it becomes even a bit ambiguous or hard to tell whether, if you have 3 frames, which frame should come before the other, right? Because there's just not really anything happening in the video. So what they did is they computed some notion of motion, and then they tried to sample tuples within those regions. And once they computed this, they sample these tuples, and then they simply create a set of positive samples and negative samples. The positive samples are simply frames that occur in sequence in the right order, and then negative tuples are created by simply shuffling the frames, right? So then you have your positive set, your negative set, and you train a classifier. And as you've seen in many cases before, what's typically done is each of these sort of images that you have, right? These can be patches, in this case they're images. They're all run through the same architecture. Their representations are combined in some way, and then a classifier is trained on top of them. Yep.
So once you've got a different model and it's how do you generalize? You put in a new video and it should be able to predict subsequent frames. Is that
Not this one, actually. Yeah, I'm not going to cover that, but there are some works that do that try to do frame prediction as a pretext task. In this case, what this model is going to be able to do is if you give it any sort of 3 frames, it's going to be able to tell you whether the frames are in the right order or not. That's kind of all it's going to be able to do.
Is that a realistic task?
Well, it's a task that was shown to do better than learning from scratch. But the goal typically with these types of representations is to learn a representation that you're going to use to initialize some other model, right? So, for example, this approach is going to be used to train these weights, right? These AlexNet weights. And then, if you want to now use these weights to initialize, for example, a video action recognition model, then these weights are going to allow you to converge to a more optimal solution, basically, in your target task. Yeah. So I haven't touched a lot on how these models are actually used too much. That might be slightly confusing, but we will get to that later on. So another kind of approach, let's say, sort of designed for video understanding is this one, where we want to sort sequences, or at least kind of once again understand permutations of sequences. And so I'll just kind of go through the schema because it's very easy to understand visually. So it's kind of a bit similar to what we just showed, right? So you have like some sequence of frames right here. You sample a set of frames from that sequence. In this case, you sample 4 of them. Then you shuffle the order somehow. So you see, for example, these red lines imply that the frames are sort of being shuffled into some other order than their actual original order, right? So you see B ends up at the end, C ends up there, etc. You have these 4 frames, they're shuffled. You apply a model to it, right? So you extract some features. Then you do some combinations of these features. It's not super important. And then once again, you're going to do a prediction task. In this case, you're predicting the permutation that was made, right? So you can see here like a set of potential permutations. And you're supposed to, the goal is to predict the permutation that was used, right? So it's a bit similar to what we saw with the jigsaw puzzle, right? With the reversion of the shuffled cells, right, that we saw for the tiger example. Whereas in this case, it's within time, right? So you're sorting through time instead of spatially, okay? And this is meant to encode and to basically encode temporal information that's useful. And then sort of a last sort of video understanding specific approach is predicting forward or backward video play. So once again, I like to kind of start off with things that are slightly complex and get to things that are really simple but very effective, right? And sometimes this is what happens through time, right? That different works build on each other and discover kind of more simple approaches to the same thing. And so in this work by Wei et al., the goal was to predict simply whether a frame sequence is progressing forward in time or whether it's been reversed. That's it. So what I think is interesting about this work is that rather than use as input RGB frames, what they use instead is optical flow frames, right? So optical flow frames you can think of as they're computed from two consecutive frames in a video sequence, for example. And what you compute from this pair is a displacement, right? So a displacement of each pixel in the original image, right? So it's giving you kind of like a flow field that's showing how each pixel is moving from one frame to the next. So it's a good signal for motion, for what motion is happening in the scene. And so for here, for example, this is probably an image maybe of somebody walking. You can probably kind of see it, because you can see there's a lot of motion in the legs. Okay? So these correspond to little vectors that are moving in the legs. And so this is the input that's used here. And what this work does is it takes these sets, it computes a sequence of optical flow frames from a sequence of RGB frames. It uses this sequence as inputs into a convolutional net. So once again, it applies each frame one by one into the network. It concatenates the representations for each of these inputs. And then it trains this very simple binary classifier on top of it, simply saying, okay, you have this sequence of frames. Is it representing a video sequence that's playing forwards or playing backwards? And simply that performs quite well on downstream video understanding tasks. So in particular, this work, I don't have any results, but this work was used as pre-training for video understanding problems, so in particular video action recognition, where the goal is you get like a video and you want to predict what action is happening within the video. So very typical examples are things like there are some sports data sets where you have a bunch of videos where each video is showing a different sport being performed. And then you want to kind of predict what's the sport, right? That's an example of a video understanding problem, of an action recognition problem. And what this work showed is that this pretty simple technique, I would say, outperforms some of the other methods we were showing before for this task. Okay, so that kind of concludes, I would say, some more early work, relatively early work. I mean, 2018 is still pretty recent, but in our age, it starts to feel a bit ancient. And then, so what I'm going to do now is go towards some works around contrastive learning, which are pretty popular right now. Before that, though, I want to just take a second to discuss briefly some of the architectures that are used. So I haven't touched on it that much, and the reason why is because most, if not all, of the methods I'm going to show are pretty agnostic to the specific architecture. They tend to come in maybe 3 flavors. You have convolutional networks, like the one you see here. So how many of you are familiar with ResNet? Right? Okay, good. So yeah, this is a ResNet. So this is a typical one that's used. You can imagine, you've seen a lot of examples of AlexNet, right? So the specific architecture is not super important, right? It can make a difference here or there, but it's not really the goal of these works. But it's just to say that they tend to be compatible with many different types of architectures. You'll also see, like later on, some works that start to come up that use vision transformers. How many of you are familiar with vision transformers, like the architecture? Great. So yeah, I won't go into it too much. I'll just say that, how many of you are familiar with transformers just generally? Okay. So maybe I don't need to go into it, but I'll just briefly mention that here the goal, so they're all on the same page, right? So transformers, like the high-level thing is that you have a set of tokens. So basically, you have some signal. It could be text, it could be audio, it could be images, vision. You find some way to tokenize them to create sort of like quantized, let's say like sets, right, that represent this signal. It could be things like a word, a subword. It could be things like an image patch. It could be other things. And then you use that to create some set of tokens. And then once you have these tokens, you apply certain, like a set of attention layers, multi-head self-attention layers over it, to give you sort of like transformed versions of the original tokens, right? And so this vision transformer is exactly that. And in particular, it's typically, I mean, the original work by Dosevitsky et al. Trained it in a supervised manner, where they had an additional token that's not related to any image patch. It's an additional token that they add, which is meant to eventually encode the class for this work, right? So that you can train it with a classification loss. So they have what they call a classification token. Okay? So this is just like a very high-level overview, just so that we're all kind of on the same page. And you'll see this model being used a bit later on as we move to more recent approaches. Okay, so closing that parenthesis, let's go on. So I promised you that I would I'd speak now about contrastive learning. So let's just talk a bit about contrastive learning in a nutshell. So the kind of high-level idea is that, let's say we have 2 images, x and x prime, that are assumed to be similar. They should be we've decided that they should be similar, right? And I mean, okay, I'll get into what I mean by we've decided in a second. And then we have another image y that is assumed to be dissimilar, okay? So you can say in some sense these are labels, right? And how do we know that? The way we typically do that in a self-supervised way is to say, I have an image x, and I'm making some modification to x such that I don't expect it to be, I expect it to be semantically similar, right? Even if there's some visual difference, right? So in this case, what I did is I took the original image, I zoomed it, and I just cropped it a little bit, right? So, but you can see that they ought to be pretty similar, right? So not much has changed, at least in terms of the meaning behind in the images. Whereas in this case, you could say, in some cases, y is similar, right? They're both mammals. They both seem maybe to be like sort of canine related. But we've decided that because it's a different image, it's going to be considered to be dissimilar, right, for the purposes of learning this representation. Okay? So we have this setup. We have these three images. And what contrastive learning wants to do is it wants to train an embedding function, phi, such that once you apply this function to your samples, it's going to project it into some embedding space such that images x and x prime are close together. So for some metric of similarity, right, it's close. And that the distance between x and y is sort of high. Okay, so that's really high-level overview. And there are many ways of kind of instantiating this high-level principle. And so for those of you who are familiar with metric learning and thinking, okay, this looks very similar to metric learning, it does, because it is. So that's just a signpost for those of you who might be familiar. And what we'll see is that this approach, and many different variations on this theme, you'll see that it performs quite well, even outperforming a lot of the kind of more ad hoc tasks I was mentioning before. So I'm just going to show you, I think, about three examples of this. And I think that's where I'm going to close off for today. So I'm going to show you, I'm just going to close out the contrastive learning section, then we can continue tomorrow. So in this work, this is seminal work from 2006 by Hadzel et al. And in this work, the authors proposed to learn this function, G parameterized by W, for dimensionality reduction, let's say, problem task. Right? So the goal is that we want to have a function that takes some input in the space R capital D and projects it into a space, maps it into a space of dimension R common D. And so to do this, it's assuming that you have some kind of distance function, D, parameterized by W. And what D does is it takes two samples, x1 and x2. So here, I apologize for the notation. I kind of just copied it from the paper, so it's not super consistent with what I showed before. But basically, x1 and x2 are two image samples, for example. Okay? And then you have these two samples. And then in this case, for example, it's just the squared loss, so the squared distance between the two. Sorry, not the squared loss between the samples, but the squared loss between the embedding of the samples, right? So you see you apply the function that you're learning, right, GW, to x1 and x2. And so now they're in this new space. And what you're saying is, okay, now that they're in this new space, I want the distance between them in this new space to be minimal, right? Well, you don't see that yet. I mean, I'm showing you the distance, but now I'll show you the loss, which will do that. So, right, so you have this decision function. It's going to tell you, I have these two samples. I'm putting them into this new space. Here's how far apart they are, right? And once you have that, you're going to define this loss, L, which is going to compute this loss over all of your tuples that you have, right? And the tuples were the ones I showed before, right? So two images that are similar, and then one image that's sort of dissimilar to the first. And the losses, so you're going to sum this loss over all the samples that you have. And this loss, the per sample loss, is what you see in equation 3, right? So I won't describe what LS and LD look like exactly, but what it's going to do is the LS is the loss for similar pairs, right? So these are the two that should be close together. And the loss is defined such that if the distance between the similar pairs is high, so they're similar but they're far apart in the space, then you want to incur a high loss, right? So that's going to encourage the model to push them closer together. And the LD, so the loss with respect to the dissimilar images, is going to be high if they're close together, right? So If you have two images that are supposed to be far apart, but they're like close together for some notion of closeness, then you're going to incur a high loss. So these are two different terms in the loss function, and you add them together, and this is your final loss. And then you compute this, you sum this over all of the samples that you have. Right, so that just kind of says what I said. And then this kind of loss function can do kind of things like this. I think this is a kind of cool visual example. So in this case, the authors took a set of images of, in this case, digits from MNIST, and they applied this learning approach. And then what they're showing here is a kind of mapping of the samples in the space that was learned, right? So this is the final embedding space. And you can indeed see that it has learned to do kind of what we wanted it to do, which is keep samples that are similar close together in the space, and keep samples that are dissimilar far apart in the space, right? So, and I think what's cool as well is that you can see that kind of like somewhere in the middle, where the 9s kind of meet up with the 4, and you see some sort of ambiguous samples where it could be a 9, it could be a 4, then they're also kind of spanning that distance between the two, okay? So you can see that even from some early work, and I'm sure there's earlier work, but even from this work, that this type of approach has a lot of potential. The next work I'll show is much more recent. So this is from 2020, from Hay et al. And it introduces the notion of momentum contrastive learning. So this work has, I think, an interesting interpretation of what we're trying to do when we're doing contrastive learning. Okay, so the interpretation is as follows. So you can think of a contrastive learning approach as a dictionary lookup method. And so let me just break down a little bit what that means. So I think almost everybody's familiar with transformers, then you'll be very familiar with the notion of queries and keys and values, but we won't use that right now. So in transformers, right, when you have like an attention layer, you have a query, you have a set of keys, and then you want to quote unquote look up. We saw the notion of dictionary lookup earlier. Here again, you want to kind of look up among these keys which key is matching your query, right? And the way you do that in, for example, attention layers is using cosine similarity or, the cosine similarity basically. And so what you do is you compute a dot product, right, between your query, Q, and some key, okay? And when you have a key that you expect to be the matching key, you want the similarity between the query and the matching key to be higher, much higher, than the average similarity between that query and all the keys that you have, okay? So in that sense, you can think of contrastive learning as very similar because many contrastive learning approaches you can consider like view 1, right? So the first image X, as I showed before, to be Q. And you can consider X prime, right? So the kind of modified version of X to be your positive key, okay? So if you think of Q and K plus as your two different views, they should be similar. And if you think of all the negative examples, right, all the things that should not be similar, that goes in the denominator there, okay? So that's how you can kind of translate the notion of, the typical notion of contrastive learning, where you have a positive pair and a bunch of negative pairs, into a dictionary lookup, where you have one key that should match and a bunch of keys that should not match, okay? So this work tried to kind of put contrastive learning in this paradigm, and then from that, there are a few kind of consequences came out. So the first is that if you think of it this way, then you see that this dictionary that's being used in the lookup is a dynamic one, right? And that's because the keys that you're generating are dynamic, because the keys are generated using a model that's constantly being trained, right, as part of the training process. The model is not constant. It's being updated as you learn. So that's one thing. It's kind of a dynamic dictionary, which is a bit weird. And then also it's dynamic because batches are updating. So I haven't gone into a ton about how this works in the context of batches, but this is just to say that all of these methods are using the mini batches, right? So you're not using your whole data set of images. You're going to use a subset of samples every time you make an update to your model, okay? And what that means is that when you're computing this loss function, as you see here, where you are, or even the loss function I showed before, right? It's very similar, right? where you have this set P. This is a set that you construct based on your mini batch, the current set of samples you have for that epoch, okay? Well, for that iteration. And so what this means is that if you think of the samples in your batch as your dictionary, that means your dictionary is changing with every batch, right? Because the samples are changing with every batch. So what that means is you have a dictionary that's changing because the model's changing, and it's changing because the batches are constantly changing, right? So that means if you're trying to learn a dictionary, you're trying to perform a dictionary lookup operation with dictionaries that are constantly changing. So that kind of dynamicity can lead to a bit of instability in the training. This is the hypothesis of this method. And so this method aims to kind of reduce that instability, or at least to make a more consistent dictionary. Any questions, feel free to ask. So the model takes this insight and it kind of uses it to make, well, the authors, they use it to make two proposals. So the first is to say, okay, if we think of this as a dictionary learning operation, then we actually want to have as big a dictionary as we can, because we know that because what this model is learning is to distinguish the true matching query, the true matching key from many dissimilar keys, the more examples of dissimilar keys it has, the better it's going to do, right? It's going to learn a more rich representation. So you want to have a batch size that's as big as possible, okay? But batch sizes tend to be limited just for computational reasons. So this work proposed to extend the batch size, i.e. extend the dictionary size, by using keys from prior batches, okay? So whereas you have your current batch, which maybe potentially has 1,000 keys, you're going to actually keep and store in some kind of memory the keys you computed in earlier batches, right? The issue with that is that, as we were mentioning, the keys from earlier batches were generated with an older model, right? And so that means that the keys are not necessarily comparable because they were not generated with the same model. So in order to avoid that, in order to minimize that issue, the authors proposed to use a sort of momentum computed encoder for the keys, as you see here, right? So they're updated in this way. So that means that the queries and the keys are generated using different models, right? So the query is generated with a model that's constantly being trained online, and the keys are being generated with a different model that's a kind of slowly varying version of the query model. So you can see here it's formulated below. So your theta is a parameterization for Q. It's a model parameters for Q, which is the query encoder. And theta K is the key encoder. And so you can see that theta K is a sort of slowly varying version of, slowly updating version of theta Q, right? And it's slowly varying because the M here is typically very large. So it's something like 0.99, right? And that means that it's being modified very slowly with respect to theta K, okay? And so adding these two things together, it means that when we are computing this contrastive learning, we take an image, it's for example X, like some view of an image, and then it has it computes a key, the positive key, which is some augmented view of an image. For example, the image I showed of like the jackal, that's a bit more cropped. And then as negatives on the bottom, it has a full dictionary size, right, which is now a much broader, a much larger dictionary than you might have in one typical batch. And what this work showed is those two things allows to train a representation that's quite effective as well. So I think I'm out of time. Yes, I didn't get to the end. So what I think I'll do, I think we'll stop here for now. And then tomorrow we'll just continue at this point. I kind of want to finish this, but I think we'll just have to jump right into it. So hopefully, it sticks a little bit. So yeah, so let's leave this here for now, and then at 11:30 tomorrow we'll come back to it and continue with contrastive learning.